The temperature at some winter research stations in the Arctic can fall below -40 degrees Celsius, a level where exposed skin can freeze in less than 5 minutes. This is the story of the life of Arctic field research itself, how it was born from curiosity and strategy, how it grew into a global system of ice stations and weather radars, and how the experience of isolation, cold, and uncertainty shaped the people who worked inside it. Long before satellites or climate models, the Arctic existed mostly as a blank space on maps. Navigation charts of the late 19th century showed coastlines, but very little knowledge of the interior or the behavior of the polar atmosphere. Nations with northern coastlines, especially the United States, Canada, and Russia, recognized that the region held strategic and scientific importance. A lesser-known fact, early Arctic expeditions in the late 1800s often lost more than 30% of equipment to ice damage, forcing explorers to improvise tools from shipwreckage or sled parts. The birth of modern Arctic research came from two pressures. One was curiosity about weather systems that began over the polar ocean and later affected Europe and North America. The other was military concern during the early years of the Cold War, when aircraft and missiles could cross the pole in only a few hours. A lesser-known fact, during the 1950s, the United States funded a chain of radar and monitoring sites known as the Distant Early Warning Line, stretching more than 5,000 kilometers across the Arctic to detect incoming aircraft. In those early decades, research teams were small. A handful of meteorologists, engineers, and radio operators would occupy a remote station for months at a time. The equipment was basic: wind gauges, ice thickness drills, atmospheric balloons, and diesel generators that ran continuously. A lesser-known fact, early weather balloons launched in the Arctic often burst at lower altitudes because rubber becomes brittle below -30 degrees Celsius, forcing engineers to redesign balloon materials for polar use. Childhood of the system, if we imagine it like a living thing, was rough and experimental. Teams learned quickly that the environment punished small mistakes. Metal tools could shatter like glass when struck against frozen surfaces. Fuel lines clogged as diesel thickened. A lesser-known fact, one of the earliest design compromises in polar equipment was the switch from standard lubricants to synthetic oils that remained fluid at -50 degrees Celsius, a change that dramatically reduced engine failure. Training of personnel became its own science. Researchers heading north were taught survival techniques, how to build wind shelters from snow blocks, how to recognize frostbite before nerve damage occurred, and how to navigate in conditions where visibility could fall to less than 10 meters. A lesser-known fact, early polar survival courses introduced in the 1960s required trainees to spend 48 hours outdoors in controlled blizzard simulations, learning to manage shelter and ration heat. Small changes mattered. Heated instrument housings were developed so delicate sensors would not freeze solid. Radio antennas were mounted higher to prevent snow accumulation from blocking signals. A lesser-known fact, early Arctic radios frequently lost power because batteries lose up to 60% of capacity at extreme cold, leading to the development of insulated battery boxes warmed by generator exhaust. As the decades passed, the research effort grew. Stations expanded in number and complexity. Aircraft began delivering supplies regularly during the brief Arctic summer. Icebreakers carried laboratories across the frozen ocean to study sea ice and currents. A lesser-known fact, the U.S. Coast Guard icebreaker USCGC Polar Star can break through ice more than 2 meters thick, allowing researchers access to regions that were previously unreachable. With growth came logistics. Every kilogram of equipment had to be transported thousands of kilometers. Fuel shipments alone often determined whether a station could operate through the winter. A lesser-known fact, some remote Arctic stations burn over 100,000 liters of diesel per year, mostly to power generators and heating systems necessary for survival. Manuals multiplied. Maintenance schedules were written in thick binders. Spare parts inventories were carefully tracked because replacement shipments could take months. A lesser-known fact, during winter darkness in the high Arctic, aircraft cannot safely land for weeks at a time, meaning teams must rely entirely on stored supplies. By the time satellites entered the picture in the 1970s and 1980s, the system had matured into something complex. Weather data from ground stations fed directly into global forecasting networks. Climate scientists began using long records of Arctic measurements to understand patterns of global warming. A lesser-known fact, Arctic temperatures have risen roughly 2 to 4 times faster than the global average over the past several decades, a phenomenon known as Arctic amplification. The peak of the system came when field research, satellite monitoring, and international cooperation worked together. Teams from multiple countries shared ice core samples, ocean current data, and atmospheric measurements. A lesser-known fact, deep ice cores drilled in Greenland contain air bubbles more than 100,000 years old, allowing scientists to analyze ancient atmospheres. Life at a research station during that peak era could feel both routine and surreal. Outside, mind would reach 80 kilometers per hour, blowing snow horizontally across endless white terrain. Inside, computers and lab equipment hummed quietly. A lesser-known fact, prolonged darkness in polar winter can affect circadian rhythms so strongly that many researchers use artificial light schedules to maintain sleep cycles. And then there were the storms. Arctic blizzards could erase the horizon completely. Visibility sometimes fell to near zero, creating what pilots call whiteout conditions. A lesser-known fact, whiteout occurs when diffuse light reflects off snow and clouds simultaneously, eliminating shadows and depth perception. Imagine a team member stepping outside during one of those storms. Snow strikes the face like needles. The wind roars loud enough to drown conversation. Shapes appear and disappear at the edge of vision. A lesser-known fact, in strong blizzards, drifting snow can accumulate more than 1 meter in a single night, burying equipment and blocking station doors. Such conditions affect the mind as much as the body. Isolation, darkness, and constant noise of wind create psychological strain. A lesser-known fact, studies of polar researchers show increased stress markers and sleep disturbances during long winter deployments. Sometimes a person in that environment sees something unusual, a moving shadow, a distant shape shifting through the snow. Often the explanation is simple: drifting ice blocks, blowing debris, or optical illusions created by snow crystals in the air. A lesser-known fact, one common polar illusion is the fata morgana, a type of mirage that can make distant objects appear distorted or floating above the horizon. Yet those moments become stories. A team member might report movement in the blizzard. Others step outside to look. Nothing is there except wind and endless white. A lesser-known fact, strong Arctic winds can carry chunks of ice or snow large enough to mimic moving figures at distances beyond 50 meters. The cost of the work remains real. Frostbite injuries still occur despite modern gear. Equipment failures can leave teams temporarily without power or communications. A lesser-known fact, frostbite risk increases dramatically when wind chill drops below -28 degrees Celsius, a threshold commonly reached during polar storms. Over time, the role of ground stations began to change. Satellites could gather data across vast areas without human presence. Autonomous sensors were dropped onto drifting ice floes to record temperature and salinity. A lesser-known fact, modern drifting buoys can transmit data continuously for 2 to 3 years before battery depletion. Some older stations closed, others shifted focus towards specialized climate research or environmental monitoring. A lesser-known fact, several Cold War radar sites in the Arctic were decommissioned after the 19th.
More than 1,000 automated weather stations now operate across the Arctic region, quietly recording wind, pressure, and temperature every hour of every day. The strange part is that many of those stations exist because of the same problem that created the earliest polar expeditions. Nobody can fully understand global weather without understanding the cold engine at the top of the planet. The life of Arctic research did not stop once satellites appeared. Instead, it entered a different phase, one that depended less on heroic exploration and more on networks, coordination, and patience. Scientists began treating the region like a living laboratory where small measurements accumulated into decades of evidence. A lesser-known fact, the National Science Foundation funds long-term Arctic observing programs that are designed to operate for 20 years or more, because short studies cannot capture slow climate shifts. Early experiments of this mature phase often involved drilling through sea ice to deploy ocean sensors. Researchers lowered instruments into water columns thousands of meters deep to record temperature and salinity. A lesser-known fact, Arctic ocean water layers can differ in temperature by only 0.5 degrees Celsius, yet those small differences strongly influence sea ice formation. Inside research stations, the routine became almost ritual. Wake up, check instruments, transmit data, repair equipment damaged by cold or wind. Outside the windows, the landscape rarely changed, but inside, the logs of measurement numbers slowly built a picture of a changing climate. A lesser-known fact, continuous Arctic records show sea ice thickness in some regions declining by more than 40% since the late 1970s, although estimates vary depending on location. The environment continued to shape every decision. Equipment had to survive conditions that would destroy most machines. Circuit boards required heating units. Plastic components had to be replaced with materials that would not crack in extreme cold. A lesser-known fact, certain polymers used in standard electronics become brittle below -35 degrees Celsius, forcing engineers to design Arctic-specific housings for sensors. Even clothing became a piece of technology. Multi-layer suits, insulated boots, and heated gloves allowed researchers to work outside for short periods without injury. A lesser-known fact, modern polar field suits can trap enough heat to maintain body warmth for 30 to 40 minutes in temperatures near -50 degrees Celsius if wind exposure is limited. Still, the psychological side of isolation remained difficult. Months of darkness and the constant sound of wind created an environment unlike any other workplace on Earth. A lesser-known fact, psychologists studying polar teams often compare winter research stations to spacecraft simulations because both involve confinement, isolation, and delayed communication. That mental strain sometimes sharpened imagination. In a blizzard, visibility collapses to almost nothing. Snowflakes reflect light in every direction, erasing edges and shadows. A lesser-known fact, during severe Arctic whiteout, human depth perception can fail so completely that a person may misjudge distance by hundreds of meters. In those moments, the landscape can appear alive. Drifting snow forms shapes that move and disappear within seconds. Ice ridges creak under pressure as the frozen ocean shifts. A lesser-known fact, pressure ridges in sea ice can reach 10 meters in height, created when large sheets of ice collide and push upward. Researchers sometimes report strange sounds during storms, deep groans, cracks, and low rumbles carried through the wind. The explanation is usually mechanical or geological. A lesser-known fact, expanding and contracting ice sheets produce acoustic vibrations that can travel several kilometers across frozen terrain. Yet stories spread easily in remote environments. A single unusual observation becomes a topic of conversation for days. Someone claims they saw movement beyond the instruments. Another swears they heard footsteps outside the station wall. A lesser-known fact, fatigue and disrupted sleep cycles increase the likelihood of visual misinterpretation during polar night conditions. The peak effectiveness of Arctic research arrived when these human observations combined with hard data. Satellite imagery confirmed patterns seen by ground teams. Ocean sensors validated theories about melting ice and changing currents. A lesser-known fact, Arctic ocean water layers can differ in temperature by only 0.5 degrees Celsius, yet those small differences strongly influence sea ice formation. This integration of technology and fieldwork revealed something important. The Arctic was changing faster than scientists expected. Ice that once survived multiple summers began disappearing in a single season. A lesser-known fact, multi-year sea ice, ice older than 2 years, has declined dramatically, making up a much smaller portion of the Arctic pack today. For the researchers inside those stations, the data had personal meaning. They were watching a transformation in real time. A lesser-known fact, the Arctic summer minimum area of ice has shrunk by millions of square kilometers since satellite monitoring began in 1979. But every system eventually faces limits. Maintaining remote stations became expensive. Fuel deliveries, aircraft support, and specialized equipment required large budgets. A lesser-known fact, operating a single remote polar research station can cost several $1,000,000 per year, depending on logistics and staffing. As autonomous technology improved, some missions shifted towards robotic instruments. Unmanned drones began mapping ice flows and glacier movement. A lesser-known fact, Arctic research drones can operate in temperatures down to about -20 degrees Celsius, though colder conditions require heated battery systems. Older stations closed or reduced staff. Instead of dozens of researchers living year-round in isolated buildings, smaller teams rotated through seasonal deployments. A lesser-known fact, many Arctic field sites now operate primarily during the brief summer window of June through August, when aircraft access is easier. Even with these changes, the legacy of decades of work remained embedded in scientific databases and climate models. Numbers recorded by researchers in the 1960s and 1970s are still used today. A lesser-known fact, long-term datasets from polar stations help calibrate global climate simulations that run on modern supercomputers. And the stories of life in those stations continue circulating among scientists. Stories about blizzards that buried equipment overnight. Stories about instruments frozen solid despite heating units. Stories about a team member who stepped outside during a storm and thought they saw something moving in the snow. Most of those stories end the same way. Someone investigates the shape in the distance. The wind shifts. The snow clears for a moment. Nothing is there except ice, darkness,
and the endless Arctic horizon. Because the real truth of polar research is not a hidden creature in the blizzard. It is the long human effort to observe a place that resists observation, a region where cold reshapes machines, weather erases certainty, and even the eyes of trained scientists sometimes struggle to interpret what they see. The Arctic doesn't need monsters to feel mysterious. The scale of its storms, the silence of its winters, and the fragility of the data collected there are enough. And that is the quiet ending of the life story of Arctic research, a system built from curiosity, hardened by cold, and remembered not for what might have been seen in a blizzard, but for what humanity learned by staying long enough to measure it.